Hey everybody, it's Mr. Kolu, and I'm back with some Kolu math. And today we're going to be taking a look at combinations. A combination is an arrangement where order does not matter. And that should sound kind of familiar, actually. It's very similar to our definition for permutations, which are arrangements where order does matter. Combinations are very similar, except that order does not matter. And we'll get deeper into the relationship between the two of these later on. But back to combinations. Remember, their order does not matter, okay? Always key to remember those nots. And usually they show us this equation, which a while back might have been kind of frightening for us. Nowadays, we know we just have to plug in those N and those R's and just kind of follow it out. So not that frightening, but let's take a look at it from the abstract first, and then we'll delve into the numbers here. So we're going to start by visiting my very favorite pizzeria, Hungry Joe's. When we go inside, we see that there's basically three courses set up. We have an appetizer course, a pizza course, and a dessert course. Let's begin with the appetizer course. The question arises, how many different platters can we make? And we've got 5 different options there for appetizers, and we're going to choose 2 of them. So it's a 5C2. But let's not worry about those numbers right now. And let's just focus on thinking about this from the sort of the conceptual standpoint. So I could have wings with chips and dip. I could have wings with nachos. I could have wings with fries. And I could have wings with potato skins. So that was 4 different combinations. And we can chart those out using abbreviations. And I can actually do the same for the other items on the menu. I could have chips and wings, I could have chips and nachos, I could have chips and fries, and I could have chips and potato skins. The same is true for the rest of the items.
Excuse me, sir.
Hey, Joe. Hearing from you a bit earlier than usual.
Can you tell me, is there any difference between wings with chips and dip or chips and dip with wings?
No, Joe, I don't think there is any difference.
Or is there any difference between chips and dip and potato skins, or potato skins and chips and dip?
Kind of think I know what you're getting at here, Joe.
Well, then why are we leaving them on the board? It seems like we have a bunch of doubles.
Yeah, Joe, actually you're right. Because with combinations, those arrangements, the order does not matter. It doesn't matter which I order first or which goes first on the plate. I'm going to have the same meal. So we can actually go through there and remove the duplicates. If we look at the first item, wings and chips and dip, let's see if that item comes up again. And sure enough, it does right below. Chips with wings. Okay? We can do the same thing for wings and nachos. Find all the matching pairs, and there's only one. Nachos and wings. Wings and fries. Fries and wings. Wings and potatoes. Potatoes and wings. You see that made kind of an interesting pattern there. And if you notice, that pattern continues as we go through the different options. So we're literally knocking out a pair. And when we get all finished there, you can see we're left with 10 different menu choices. So when they ask us how many different sample platters can we make, we know that that's 10, or 5C2. All right, let's move on and check out another one, and kind of think about this a little more, well, then we'll get really into the numbers. Here we have fresh pizza, and we want to know how many different 2-topping pizzas can we make. Well, there are 7 different toppings. We're going to select 2 of them, so that's a 7C2. And like I said, we're not going to worry about the numbers right now. Here are different types of toppings, and the different kinds of combinations that can be made are listed here. And again, if we cancel out the doubles, you'll notice that we lose half of our options. So we go from 42 to 21. And when we try to answer that question, how many different 2-topping pizzas can we make? We know the answer there is 7C2, or 21. So let's go ahead and take a look at the math here real quickly and see if we can understand what's going on. We know that NCR means the number of combinations that can be made from N items when you're selecting R. So in the case of 7C2, we know that's the number of combinations that can be made from 7 items selecting 2. When we think about NCR, here's the equation they give us. N factorial over R factorial times the quantity N minus R factorial. Again, might have been frightening initially, but we know all we have to do is plug in, so it's not too complicated. So if we had something like 7C2, we could go ahead and plug in 7 and 2, and then we could solve it out. Let's start by doing the factorial on the top. Okay, and writing out the expansion there. Let's deal with the parentheses on the bottom. 7 minus 2 is 5. Okay, let's deal with those factorials. 5 factorial and 2 factorial. And if you notice, once we expanded out those factorials, that we have sort of a repeat here. Same items on the top as we do on the bottom, which is really cool because what we can do is factor those out into their own separate fraction, if you remember the rules of multiplication with fractions. And since it's the same numbers over each other, that's 1 over 1 or 1. So we're left with just the front two parts of our formula. Let's go ahead and solve that. 7 times 6 over 2 times 1. That's 42 over 2, or 21 total. We can also look at the math from the earlier problem. We had 5 different options for our appetizers. There were 2 that we were going to select for our dish, and we can go ahead and plug those in, go ahead and substitute, and the same deal happens here. We've got these 3 times 2 times 1 over 3 times 2 times 1, so we can remove that back half, and that leaves us with 5 times 4 over 2 times 1, which is 20 over 2, or 10. When we're looking at that generic rule, that NCR, we notice that that formula looks really similar to the formula for permutations. And the only difference between them is the r factorial in the denominator. And if we factor out that r factorial into a separate fraction, we can actually replace the n factorial part of the equation there with NPR, multiply it by 1 over r factorial, and that gives us NPR over r factorial. The combination is really just a permutation divided by the number of objects selected as a factorial. And if you remember our shortcut for solving permutations, starting at n, counting down our numbers, and then multiplying them together, we can actually use that exact same rule when we're solving combinations using this equation. I can go ahead and start at n, so in this case 9, count down our numbers, so 3, and then multiply them together. I can do the same for the denominator, except for the denominator I'm just doing a straight factorial. So I'm going to start with r, I'm going to count down our numbers, and then I'm going to multiply. Okay, go ahead and finish up the math there, reduce that fraction, and that gives us an answer of 84 different combinations if we're doing a 9C3. And if you notice, the 9P3 is 504, and the 9C3 is 84. And those numbers demonstrate that a combination is a permutation with the doubles taken out. Just real quickly, to do a 7C4, all we have to do is 7, count down 4 numbers, multiply them together, and then do 4. Count down, multiply them together. Just that simple to solve a combination. Okay, let's look at this last one here. We've got a pick 3 sundae, which means we get to pick 3 of those flavors. We want to know how many different pick 3 sundaes could we make? Well, there's 5 different options, and we're going to choose 3 of them. So it's a 5C3. We can just go ahead and apply that directly into our formula. 5 factorial over 3 factorial times the quantity 5 minus 3 factorial. We can go ahead and do that out using our shortcut method, and we have our fraction. We reduce that. We know that there's 10 possible combinations for that sundae deal. Just to be sure, let's check our work with the old method of writing out the combinations. So if we start with vanilla, here are our different possible combinations. And if you notice, we're choosing 3, so we're going to get more options as we have to match more flavor combinations with vanilla. And the same is true with the rest of them. Okay, and you can chart them all out if you want to figure them out. When we begin to knock out those duplicates, you'll notice that there's a higher percentage than there were in the earlier problems. And that's because we have a higher rate of duplicates when we're combining 3 items. When we finally knock out all the duplicates, we're left with 10, which is exactly what we got with the numerical solution. Okay, so combinations versus permutations. Remember that a combination is an arrangement where order does not matter, and a permutation is an arrangement where order does matter. Combinations are good for groups, teams, piles, anything that doesn't matter what order they're placed into those groups. And a permutation, they're good for ordered lists or competition results, where it matters what order you're selected in. First place is better than third place. Okay? If that's the case, you've got a permutation. All right, so let's take a look at this example and figure out if it's a combination or a permutation. Yvette is throwing a blowout Sweet 16 party. She has 14 VIP girls, but only 5 can fit with her in the limo. How many different entourages could Yvette arrive with? All right, does it matter what order they get in the limo? Well, it may seem like it does, but as long as they've got a ride, it really doesn't matter. So that's a combination. And we can go ahead and plug those numbers in. We've got 14 VIPs, we're choosing 5. 14C5 is 2002. Let's take a look at another one. There are 12 horses in a horse show competition. The top 3 winning horses receive money. How many possible money-winning orders are there for a competition with 12 horses? Does it matter what position you get in a competition like that? Yeah, if you're in first place, you're going to win more money. So order does matter. We've got what's called a permutation. Since it's a permutation, let's go ahead and use P. 12P3, we get 1320. 12 horses, we're choosing the top 3. All right, on to another one. The New Jersey International Film Festival had 324 submissions for their 2008 festival. If the festival selects 6 films, how many different lineups could the film festival screen? Okay, does it matter what order those guys are selected? No, not at this point. They're just trying to get into the contest, so it doesn't really matter. It's a combination. And we can go ahead and use 320C6 or 1,533,615,890,000. Okay, that's a lot of different combinations. On an American League Baseball team, there are 8 starting players on the field and a designated hitter that can be picked from the rest of the roster. If each 8 players on the field get a spot, as well as a spot for the designated hitter, from a possible 10 players on the bench, how many batting orders are possible? Right, that's a permutation. So let's go ahead and pop it in the equation. 1,814,400 different batting orders are possible with a team of 10. Isn't that kind of crazy? All right. Well, that was a lot of fun, guys. I'll see you guys soon for some additional math content, and have yourself a great day.